So now I think we have been dealing with the Klein-Gordon field, Klein-Gordon equations and its solutions and everything essentially. So and we saw what are the pathologies and what are the problems related if you believe if you do the same techniques as you use in non-relativistic quantum mechanics, like you try to build wave functions, or if you try to build, say for example, scattering problems in in the relativistic quantum mechanical framework, exactly in the same way what you do in the non-relativistic framework. Good. And so we saw that it leads to problems and everything essentially. So we want to move to something else essentially. Is there any way out? Now, so there are ways out essentially. One of the ways out was people started thinking that maybe the problem lies with the way we started with the dispersion relation itself, essentially the relativistic dispersion relation essentially. Okay. So today we will start with something called the Dirac theory essentially. So now the point of Dirac was that Dirac started with the idea that the problem lies perhaps with the quadratic dispersion relation. Now this okay, these is nothing but that what it means is that essentially the problem lies with the relation E square is equal to P square plus M square, because in quantum mechanics all the operators are linear. Okay. So all the properties are linear, all the operators are linear. So if you, the moment you try to write an operator essentially the physical quantity in terms of an operator, you will end up having both positive and negative states, and then you have to take the square root, and so you have the relation in this particular fashion. In this particular fashion. Now this is the problem essentially. Okay. Maybe this is the problem, that because this is a quadratic relation, and now the moment you put it in terms of operators essentially, both the signs of the square root are appearing in the solutions essentially. Both the signs are appearing in the solution. Now how do you get rid of this? And the second thing was that, okay, okay, now this is the problem essentially, and then the bigger thing which bothered Dirac was that the probability density or rho, which is phi star del by del t phi minus phi del phi star by del t could be negative. So the negative norm, okay, negative norm, okay, of the probability, okay, is something negative norm which bothered Dirac. Now Dirac thought radically a very completely radical solution to this problem essentially. He completely thought of as completely radical solution, which is a bit amazing. So how do we solve this problem essentially? Both these problems we have seen essentially that it leads to problems especially when we put in interactions. Now the way Dirac tried to solve this problem, which is very interesting, is to assume that there is indeed a linear relation of this type. Now the moment you write this, essentially you see that obviously this is wrong in the sense that this is not true from relativity point of view. But then now you put a p bar essentially and m. So this is a vector. So this means that this has 3 indexes 3 px, py, pz and m. Now how do you make this correct? So what he did was that this may not be a equation, okay. The main assumption what Dirac made was that this is a such a dispersion relationship exists, but such that it multiplies with some matrices. Essentially this is not a quantity which is scalar, okay. This is a major crucial step which he has considered, essentially that this is not a quantity which is scalar, and that means these are not E is on the left hand side a is a scalar obviously, but the right hand side contains some other quantities which he called them as alpha bar dot beta, okay. Some other quantities which are called alpha and beta matrices, okay, alpha and beta matrices, okay. Now the moment they become matrices, he asked the question that is such a relation is still valid, and if such a relation is valid, what are the conditions on alpha and beta? So the point is that he took a scalar equation, okay, which is not valid, but said that, okay, he took a scalar which is not valid, but he multiplied them with matrices, okay. He took a scalar equation which is not valid, but whose square is valid, and so he wanted to get rid of this square root. So he assumed a linear relation, and this linear relation is valid. Instead of scalar quantities, he made them into matrices. Essentially he put them as alpha bar dot p bar. So in a way we can write it this as is equal to alpha I times pi, okay, plus beta m. I is equal to for x, y and z. Okay. Now then he asked the question, if such a relationship valid, essentially suppose if such a relationship is valid, if I multiply P with some matrices and B with some matrices, if this relationship is valid. Now how do you know that this such a relation can exist with certain values of alpha and beta? Of course it has to satisfy the relation E square is equal to P square plus m square. So if you start with an E, you should get back E square is equal to P square plus m square. So if you start with an E of this type, you should get back E square is equal to P square plus m square. Now this E square, now putting this into here, it gives me alpha I pi plus beta m whole square should be equivalent to P square plus m square essentially. So alpha square, okay. So what are the conditions, okay, because left hand side is equal to E square, okay, the left hand side is E square essentially. So you have the condition P square plus m square is equal to alpha I pi plus beta m whole square. Equating these two, okay, equating these two, you end up having the following condition essentially, okay. Now let us expand this. So beta square, the first thing is the coefficient of m square should be 1. So that means that you have beta square should be equivalent to 1. The second thing is alpha I times beta, so this you can expand it this will become alpha I square, okay, pi square plus beta square m square plus alpha I beta pi m plus beta alpha I pi m. Okay. Now first thing is beta square should be equivalent to 1, alpha square should be equivalent to 1 essentially. Now alpha I alpha j should be there, essentially there could be alpha I alpha j within this essentially. So plus alpha I alpha j pi pj, those terms are also allowed, plus alpha j alpha I pi pj. All these cross terms should be completely going to 0 essentially, and then you also have alpha square is equal, should be equivalent to 1, beta square should be equal to 1, alpha I square is equal to 1, beta I square term, and these cross terms should go to 0. Okay, do you okay? So the point is that you have alpha I beta plus beta alpha I is equal to 0. Now this can be written in terms of an anti-commutator relation. First thing you notice that alpha square is equal to 1, beta square is equal to 1. Okay. At this level it looks like this can be satisfied by simple matrices, simple complex numbers or something essentially. But the moment you come to the second part, which is essentially alpha I times beta plus beta times alpha I, you notice that you can re-express this in terms of anti-commutation relations. Alpha I beta is equal to 0, and this will lead to the conclusion that this should be matrices, alpha and beta should be matrices. Anyway assumed, okay, we started off by saying that these should be matrices essentially. Okay. So and the second condition is alpha I alpha j plus alpha j alpha I, the cross terms should also be equal to 0. This also insists that alpha I. Okay. So now the question is, what are these alpha and beta essentially? What are these operators essentially? So to begin with, you started off making this huge assumption essentially. Okay, you made this huge assumption essentially that it's a linear dispersion relationship, and alpha and beta are some sort of operators or matrices essentially. Okay. And then proceeding further, you end up having the conditions on alpha. So the first condition is beta square is equal to 1, alpha square is equal to 1, alpha beta is equal to 0, beta alpha is equal to 0, alpha alpha j is equal to beta alpha j is equal to 0. So this gives you the conditions that the commutation relations, the anti-commutation relations between alpha matrices should vanish. Okay. They should be anti-commuting. Okay. These are the conditions you will end up having on the alpha and beta matrices, and as long as these alpha and beta satisfy these conditions, you have a solution which is linear for the dispersion. E is equal to alpha times p plus beta times m, essentially you have that relations. It turns out, okay, matrices which satisfy the above conditions can be found. and the minimum dimension of such matrices is dimension 4. Okay. Now, how do we get dimension 4 essentially? So, the moment you see this, you see that alpha square and beta square is equal to 1. Now, alpha square and beta square is equal to 1, you can apply the trace theorems, and essentially that you can look at various conditions. Essentially you will see that alpha square is equal to 1. So, det alpha square is equal to 1. So, the first condition you will see, why do you get dimension 4 is equal to beta square is equal to 1. So, alpha I square is equal to 1. So, determinant of beta square is equal to the condition 1 essentially. How do you reach the dimension should be 1. So, alpha I square is equal to 1, beta square is equal to 1. So, determinant of each alpha, so there are 3 matrices, alpha matrices, I is equal to 1. So, all of them should have determinant square should be equal to 1. Applying the determinant square on both sides, you have identity on the left hand side, identity on the and so the left hand right hand side. So, you should be determinant of unit matrix is 1 essentially, and so the determinant of alpha I square should also equivalent to 1. So, if the determinant is equal to product of eigenvalues, so if the product of eigenvalues, determinant of alpha I is equal to lambda 1 to lambda n is equal to 1. So, that means so the lambda I of the alpha matrices should be equivalent to plus or minus 1, and this also fixes the dimension should be equivalent to even. You cannot have odd dimensions essentially, okay, because if you have if the eigenvalues are plus minus 1, there should be equal number of plus there should be you cannot have so you cannot have odd dimension matrices. Say for example, if you have a lambda 1 times lambda 2 times lambda 3 is equal to plus 1, okay. Now, if the eigenvalues are minus 1, that equation will not work essentially, because you know minus 1 is also a solution essentially. So, this fixes, so you cannot have or unit matrices, for example one dimensional matrices, that also says that if we have eigenvalue minus 1, that equation is valid essentially, invalid essentially. So, this possibility of having the eigenvalues both only to be plus and minus 1, because the determinant is always this one, rules out that these matrices should be odd dimensional. So, the dimension of these matrices should always be even. So, this is one of the biggest conditions which you have. Okay. What is the second condition? The second condition is that okay. Now, you can see that if I multiply, okay, beta times alpha I times beta, you get minus alpha I. Now, where is this coming from? This is coming from this anti-commutative relations between alpha I and beta. Now alpha and beta I plus beta alpha I times beta times beta alpha I is equivalent to 0. Now you can always multiply beta on both sides, essentially beta alpha I beta plus beta square alpha I is equal to 0. This gives me beta alpha beta is equal to minus alpha I. Okay, you have this condition essentially. Now with this condition, now you take, now this automatically tells you that if I take the left hand side trace beta alpha I beta is equal to minus trace of alpha I. Okay, let me use square brackets for this trace operator, otherwise it leads to continuous. Trace alpha I. Now this I can rewrite it as trace of, okay, beta and alpha I are anti-commutating essentially. Okay, if okay, beta and alpha I are anti-commutating, I can write it as alpha I, or in other words, if I can beta square is equal to 1. So this is beta times beta, trace of beta beta. Okay, because alpha beta also anti-commutate or beta alpha also anti-commutate, essentially you get a minus sign essentially. So trace of alpha beta, trace alpha I. This is only possible, okay, this is only possible if you have trace alpha I is equal to negative of the trace of alpha I. Alpha I is one matrix, say let us take alpha 1 or something essentially, okay, I is equal to 1 2 3. Okay, for each of this thing you see that trace of alpha I is equal to 0, because trace of alpha I is equal to minus trace of alpha I. So you end up having that kind of a relation essentially, and from this you can show that the second condition is that they are traceless matrices, they are traceless matrices. So you have a condition that they are traceless matrices and even dimension. So this already puts very strong constraint and on the possible matrices you can have essentially, and their eigenvalues should be plus or minus 1 essentially. Now such matrices we already know in quantum mechanics essentially, such matrices we already know, such matrices are already known in quantum mechanics. These are the, but how many such matrices we need? We can do something similar also, show that trace of beta is equal to 0. Now how many such matrices we need? We need 4 matrices, 3 alphas and 1 beta. The matrices which we know in quantum mechanics, there are only 3 of them. They are only 3 in number and they are nothing but the Pauli matrices. They have all the properties, the Pauli matrices sigma I is equal to sigma x, sigma y, sigma z essentially. So, what are these matrices? Sigma x is equal to 0 1 0 sigma y. Okay. So, these three matrices exist, okay. These three matrices exist, okay. And so, now, so but only three of them are linearly independent. You cannot have a fourth one which is linearly independent essentially. Now, the point is that these so okay, so we can also argue in terms of mathematics essentially. How many Hermitian matrices are possible? Okay, so dimension 2 will not work. Now, there is also mathematical argument essentially. So, if we have how many Hermitian matrices in n dimensions, one has n square Hermitian matrices. Which includes unity. Now, do you all agree that these are all Hermitian matrices, right? Essentially, sigma dagger is equal to sigma essentially. Okay. So, the remaining Hermitian matrices n square minus 1. So, if n is equal to 2, you have 4 minus 1, only 3 Hermitian matrices. Okay. Now, if we have n is equal to 4, say for example, because it should be in dimension 16 minus 1, 15 Hermitian matrices are possible. Now, remember this number, we will come back to it again essentially at some point or something essentially, we will need it at some point essentially. For n is equal to 4, okay, when the dimension is 4, there are quite a few Hermitian matrices are possible, 15 Hermitian matrices, but we only need 4 essentially, we only need 4. Okay. So, we have a possibility in n is equal to 4. So, n is equal to 4, there will be a possibility of having them, and so we want to introduce, so there is a possibility of solutions essentially. So, one of the first representations essentially of the Dirac matrices where we have a solution is as follows essentially. Solutions for alpha and beta matrices, okay, and these are called Dirac matrices. Dirac matrices. Suppose if beta is equal to 1 0 0 minus 1 and alpha I, each of the alpha i's is made up of the sigma matrices, but in this particular fashion. Okay. This is the first solution which we have of the, now this will satisfy all the conditions which we have seen here for the alpha and beta matrices essentially. Okay. This will satisfy all the conditions which we have seen for the alpha and beta matrices which we have introduced. So, for the first time, okay, for the first time we have alphas, a representation for the alphas and the beta matrices in term which can satisfy the linear dispersion relationship, which is E is equal to alpha I times pi plus beta times m, where alpha and beta are given by this relation essentially. Okay. So, what we have seen is that it is possible to have a linear relationship, dispersion relation, or a linear E is equal to p plus m relation if you multiply P with matrices of dimension 4 which are given in this particular fashion, and beta is just a unit matrices with the first two entries to be of with positive unity and the next two entries to be negative unity, then it is satisfied. So, this relation. Okay. I will stop here and we will continue in the next lecture.